Good morning, students. Welcome to video lecture on microwave and optical fiber communications. Subject code U18EC709. Topic directional coupler. Directional coupler. A directional coupler is a device that samples a small amount of microwave power for measurement purpose. The power measurements include instant power, reflected power, and VSWR values. Directional coupler is a 4-port waveguide junction consisting of primary main waveguide and a secondary auxiliary waveguide. The following figure shows the image of a directional coupler. It is the image of a directional coupler. Directional coupler is used to sample the microwave power, which may be in unidirectional or bidirectional. Now here the directional coupler consists of a primary main waveguide, includes port 1 and port 2. It includes secondary waveguide associated with ports 3 and 4. It is a 4-port device, so the S matrix is of the order of 4 by 4. Now here you can observe the instant received forward and back powers. At port 1, if some power is applied, the instant power is indicated by Pi. The maximum amount of power will be received at port 2, and the received power is represented by PR. When the power traveling from port 1 to port 2, some amount of power will be coupled to port 4. The coupled power is called forward power and it is represented by PF, and there is no power received at port 3, so it is called back power represented by PB. You can represent PI, PR, PF and PB at ports 1, 2, 3, 1, 2, 4 and 3 respectively. Now the properties of a directional coupler. Ideal directional coupler. All the terminals are matched to the load, means S11 is equal to 0, S22 is equal to 0, S33 equal to 0 and S44 is equal to 0. When a power travels from port 1 to port 2, you can observe port 1 to port 2, it is 3, sorry, it is 4 and it is 3. The power traveling from port 1 to port 2, some portion of it gets coupled to port 4 but not to port 3, means here when it is traveling from port 1 to port 2, the power will be coupled to port 4 but not to port 3, means here 1 and 3 are isolated ports, so S13 equal to S31 is equal to 0. And as it is also a bidirectional coupler, when the power travels from, once again I will represent 1, 2, 4, 3 port positions. When the power travels from port 2 to port 1, some of its power gets coupled to port 3 but not to port 4, means when the power is applied at when the power input is applied at port 2, maximum power will be received at port 1 and some amount of power will be coupled to port 3. In ideal case, no power will be received at port 4, means S24 in terms of S matrix, S24, S42 is equal to 0. And if the power is instant through port 3, if the power is applied at port 3, portion of power is coupled to port 2 but not to port 1. That is 1 and 3 are isolated ports. Once again, if the power is instant through port 4, it is coupled to port 1 but not to port 2. Means 2 and 4 are isolated ports, and here port 1 and port 3 are decoupled, and port 2 and port 4 are also decoupled. That's what we discussed just now. The following parameters are to define uh, are used to define the performance of the directional coupler. The first one is coupling factor. It is the difference between incident power and coupled power in terms of dB. If it is not in terms of dB, you can use this particular formula. The next is directivity. The directivity is the power difference between PF and PB. PF and PB are in terms of dB. You can directly take the difference. This can be taken as directivity. If they are normal values, you can apply in the given formula. Here, you are taking the ratio of power, so you can use 10 log. If the ratio is in terms of voltage, in general, we take 20 log. Okay, here our discussion is with power, so always prefer to use only 10 log. If you use 20 log, that is incorrect. The next is isolation. The isolation is the difference between instant power and back power in terms of dB. If it is in terms of dB, you can directly take the difference. Otherwise, you can simply substitute in the formula. And here the relation, one more relation between uh, coupling factor, directivity, and isolation is I is equal to C plus D. For example, here you just take the ports of directional coupler 1, 2, 3, 4. Now for a particular directional coupler, the coupling factor is 20 dB and directivity is 60 dB. Means here coupling factor 20 dB means what is the amount of power coupled to when power traveling from port 1 to port 2, what is the amount of power coupled to port 4? That is Pi by 100. 1% of the power will be coupled to port 4 when the coupling factor is 20 dB. And when the directivity is 60 dB, in ideal case, there is no back power, but here Pi, PR, this PF is equal to Pi by 100 and PB is equal to, if the directivity is 60 dB, then the relation between PF and PB is equal to 10 power 6. So in terms of input power, it will be 10 power 8. Back power is very small, but in ideal case, the back power will be considered as 0. You can observe the relations what we discussed just now. The coupling factor is a measure of how much of the instant power is being sampled, while directivity is a measure of how well the directional coupler distinguishes between the forward and reverse traveling powers. A two-hole directional coupler. It is a two-hole directional coupler with 4 ports. It is the main waveguide, it is the auxiliary waveguide, port 3 and port 4. When here some two holes are created, that is why it is called two-hole directional coupler. The distance between first hole and the second hole is lambda g by 4 quarter wavelength. When the power is traveling from port 1 to port 2, some power gets leaked in the two holes. Here let us discuss the amount of power leaked in port 4 and port 3 in the next slide. Now here, the distance between these two holes is lambda g by 4, and when the power is traveling from port 1 to port 2, at port 4, two power components will be received, that is the direct power escaped from hole 2, and another part of the power escaped from hole 1 entering into the port 4. Now here these two powers gets added in phase to get the value of couple power somewhat considerable. But the amount of power which is received at port 3, that is directly through hole 1, and some portion of power escaped from hole 2 will also enter into hole 1. These two powers are in out of phase, so the difference of the power will be received at port 3. In practice, it is having some very small value, but if it is ideal case, it is 0. Now here, this is the basic operation of two-hole directional coupler. The two-hole directional coupler is designed to meet the ideal requirements of directional coupler, which is to avoid back power. You can read out the point just now. Some of the power while traveling between port 1 and port 2 escapes through holes 1 and 2, and due to in-phase component, you will get some considerable power at port 4, and due to out-of-phase components, you will get very less amount of power will be received at port 3. And hence, directivity of the directional coupler improves with the use of two holes. Scattering matrix derivation. Basically, it is a 4-port device, so the S matrix is of the order of 4 by 4. All the ports are perfectly matched with the junctions, so S11, 22, 3, 3, 4, 4 all are equal to 0. And from the symmetric matrix property, you can apply Sij is equal to Sji. And here Sij stands for scattering coefficient resulting due to input at jth port, output at ith port. If it is symmetric matrix, you can exchange the values of I and j. Ideally, the back power is 0. There is no coupling factor between the ports. One and 3. That is S13 is equal to 0, S31 equal to 0. In the same way, S24 equal to 0, S42 equal to 0. And substituting all the above points, you will get the modified S matrix as you will get the principal diagonal elements are 0, and in some other positions you will get zeros, and the S matrix is in terms of S12, S34, S14, and S23. By knowing only 4 parameters, you can determine the values of S matrix. That is, substitute in unitary matrix property, that is uh, S into S conjugate is equal to I. That is S into S conjugate is equal to I, and expand along R1C1, R2C2, R3C3, and R1C1. You will get some relations. Let us take them as 6.66, 67, 68, and 69 by comparing what we are doing here. By comparing first two equations, you will get S14 is equal to S23, And by comparing second, third equations, you will get one more relation. S12 is equal to S34, and let us assume that S12 is a positive real quantity. So S12 conjugate is also equal to P, because here P is a real value. Um, from 6.69 and 72, you will get the interrelation like this. That is by taking common P, S23 plus S23 conjugate is equal to 0. Here just now we assumed it is a real value not equal to 0. So this particular term must be equal to 0. Some x plus x conjugate equal to 0 means x must be a imaginary quantity. Let it be some S23. You just assume it as JQ. Then S23 conjugate is equal to minus JQ. And after substituting the remaining elements, you will get the S matrix of directional coupler as P, JQ, P, JQ with some zero elements in between. And here the P and Q values are in such a way that root of P square plus Q square is equal to 1. Thank you. We will meet with the next lecture.